Hi everyone. In this video, we are going to see how to find the coordinates of the incenter of a triangle when the coordinates of the vertices have been provided. If the vertices are provided, we can easily calculate the length of each side. We can simply use the distance formula to find the length of each side. Now let's suppose we have a triangle like this, triangle ABC, and the coordinates of the vertices have been provided. With this information, we have to find the coordinates of the incenter of this triangle. So what is an incenter? Well, an incenter is nothing but the point of intersection of the angle bisectors. So for this triangle, I am going to draw a couple of angle bisectors, and then the point of intersection of the angle bisectors will be considered as the incenter. Let's suppose AD is the bisector of the angle A and BE is the bisector of angle B, and let's suppose their point of intersection, which is I, that is the incenter for this triangle. And let's suppose the coordinates of I are H and K. The X coordinate is H and Y coordinate is K, and we have to find the values of H and K. Whenever we have to find the coordinates of a center of a triangle, for example, whether it's centroid or incenter or circumcenter or orthocenter, we have to use the section formula. Before we can calculate the coordinates of the incenter, we have to calculate the coordinates of a helping point. For example, in this case, I am going to take D as the helping point. Now, if we can somehow find out the ratio of BD is to DC, then we should be able to use the section formula to find the coordinates of D. And then ultimately, we have to again find the ratios of DI is to IA. And from there, using section formula, we should be able to calculate the coordinates of I. So first we want to find out the ratios of BD is to DC. Now for that I have to do one little extra construction. I am extending the side CA and then I am going to draw a line from B which will be parallel to AD. And let's suppose they meet at point P. So AD is parallel to PB. Since AD and PB are parallel, these two angles will be equal to each other. They will be the corresponding angles for two parallel lines, the angle CAD and the angle CPB. And similarly, these two angles also going to be equal because they will be the alternate angles for two parallel lines, the angle BAD and the angle PBA. Now if you think about it, AD is the bisector of angle A. That means the angle BAD will be equal to angle DAC and each of them will be half of A. And also if you look at the triangle PAB, that looks like an isosceles triangle because we have two angles equal. So that triangle is an isosceles triangle where AP and AB, they are of equal length, and that's nothing but the lowercase c unit. That's one of the sides of the original triangle. And now if we look at the two triangles, triangle PBC and triangle ADC, they will be similar triangles. Why? Because their corresponding angles are of equal size. For example, angle CAD is equal to angle CPB, and also angle CDA is equal to angle CBP. And of course, the angle C is a common angle between the two triangles. So these two triangles are similar triangles. And we know for two similar triangles, the ratio of the corresponding sides are equal. So we can say PC over AC equals BC over DC equals PB over AD. And then I'm going to use the first part of the proportion. And from there, we can say PC over AC equals BC over DC, which turns out to be PA plus AC over AC, because PC can be written as PA plus AC. And similarly, BC can be written as BD plus DC. And from here, we can say C plus B over B. In place of PA, I am writing C. In place of AC, I am writing B. And that is equal to BD over DC plus DC over DC. BD plus DC over DC can be written as BD over DC plus DC over DC. And from here, we can write it as C over B plus B over B equals BD over DC plus 1. And again, from here, we can say C over B plus 1 is equal to BD over DC plus 1. And from there, we can say BD over DC is equal to C over B. That means the ratio of BD is to DC is actually C is to B. And that's a very important property of the angle bisector, that it divides the opposite side in the ratio of the two sides that contain the original angle. So in this case, the original angle is angle A. It is contained by the sides B and C, and it divides the opposite side, which is the BC side, in the ratio of C is to B. Closer to the BD side is the side C and closer to the DC side is the side B. So you can easily remember that BD is to DC is equal to C is to B. With the help of this ratio, we should be able to calculate the coordinates of the point D. And also, in the next step, we are going to need the length of BD to be able to calculate the coordinates of I. So let's calculate the length of BD. And for that, we are going to first calculate the length of DC and then we'll calculate the length of BD. We just found that BD over DC is equal to C over B. and BD can be written like this: BC minus DC over DC is equal to C over B. And from there we can write it like this: BC over DC minus DC over DC is equal to C over B. The DC over DC will become 1. So in the next step, in place of BC, I have noted A, that's the side length A, over DC minus 1 is equal to C over B. And from here we can say A over DC is equal to C over B plus 1, which is nothing but C plus B over B. And from here, if we flip the ratios, we can say DC over A is equal to B over B plus C. And then we are going to multiply both sides by A. Then DC will be equal to A times B over B plus C. So we have been able to calculate the length of DC. And now calculating the length of BD is very easy, because BD will be A minus DC. And if we simplify this, we'll get the value of BD like this. It will be A times C over B plus C. So we have been able to find the length of BD, which is AC over B plus C. Next, we are going to find the ratio of DI is to AI, and for that I am going to use the little space up here on the right hand side. If you consider the triangle ABD, there BI is an angle bisector for that little triangle ABD. And for that, can we say that DI over AI can be written as BD over BA? We know that for a triangle, the angle bisector divides the opposite side in the ratio of the two sides that contain the angle. In this case, the angle is B and the two sides are BD and BA or AB. So we can say the ratio of DI is to AI will be equal to the ratio of BD is to BA, and that's exactly what I have noted here. And that can be written as AC over B plus C, because we just calculated the length of BD, which is AC over B plus C, divided by BA. BA is nothing but the side length C. So I have noted it as AC over B plus C, that is for BD, divided by BA, for which I have noted C. And if we simplify that, that becomes A over B plus C. So you can see that DI is to AI is actually A is to B plus C. And that is another very interesting property of the incenter, that the incenter divides an angle bisector in this type of ratio. And what is that ratio? Well, the ratio is actually the opposite side of the angle is to the sum of the two sides that contain the angle. In this case, if we consider AD as the bisector of the original angle A, then the incenter will divide AD in the ratio of A is to B plus C. Alright, so we have obtained all the ratios that we need to calculate the coordinates of the incenter. So now let's get started with the derivation. And now if you think about the point D, the x coordinate of D can be written like this. I am simply using the section formula for internal division, because we know BD is to DC is equal to C is to B. So I am saying that C times x sub 3 plus B times x sub 2 over B plus C, that will be the x coordinate of D. And similarly, we can say that the y coordinate of D can be written as C times y sub 3 plus B times y sub 2 over B plus C. So we have been able to find the coordinates of the point D. Now let's take a look at the original diagram. We have already been provided with the coordinates of the point A, and we have been able to determine the coordinates of point D, and also we have been able to determine the ratio of DI is to AI. So now we can easily calculate the coordinates of the incenter I. We are going to use the section formula again. So for the x coordinate of the incenter, which is noted as H, can be written as A times x sub 1 plus B plus C times the x coordinate of D. So all I am doing is I am saying A times the x coordinate of point A plus B plus C times the x coordinate of point D over A plus B plus C, because that's the ratio of DI is to AI. DI is to AI is actually A is to B plus C, and that is why I am using the section formula to calculate the x coordinate of the incenter. And if we simplify this a little bit, it is going to look like this. It will be A times x sub 1 plus B times x sub 2 plus C times x sub 3 over A plus B plus C. And that is the x coordinate of the incenter. And similarly, let's calculate the y coordinate of the incenter. Using the section formula again, I have calculated the y coordinate of the incenter, and it turns out to be A times y sub 1 plus B times y sub 2 plus C times y sub 3 over A plus B plus C. And those are the coordinates of the incenter of this triangle. Next, we are going to take a situation when the triangle is an equilateral triangle. If the original triangle ABC is an equilateral triangle, then all three sides will be of equal length. And in that case, let's see what happens to the coordinates of the incenter. we can write the value of h like this. In place of b and c, I am using a because all the sides are of equal length. So everywhere for the side lengths, I am using lowercase a as the side length. So h can be written like this, and if you carefully look at it, it actually becomes x sub 1 plus x sub 2 plus x sub 3 over 3. And similarly, I am going to calculate the value of k, and that also turns out to be y sub 1 plus y sub 2 plus y sub 3 over 3. Now think about these two values here. Do they look like the coordinates of the centroid of a triangle? In fact, that's exactly what it looks like. It looks like the coordinates of the centroid of this triangle. So, as you can see, when the triangle is an equilateral triangle, the coordinates of the incenter and the coordinates of the centroid, they are exactly identical. That means both the points are coincident. I mean the incenter and the centroid, they are exactly the same point for an equilateral triangle. And this is a very important property of equilateral triangle, so I thought I will just present it in this video, that when the triangle is an equilateral triangle, their incenter and centroid will be the same point. This brings us to the end of this video. I hope everything made sense. Thank you for watching. See you in the next video.